上课之前说一下期中考试的成绩已经出了，大家总的来说考的都很不错，但是我们不公布成绩，如果你们感兴趣的话，自己可以去互相问。开始上课。So last time we discussed spinners. We define spinner as a particular representation for range group. So we think about the decomposition of the range group as two as you do. Then the representation can be classified as two half integers, let's say m and n, each corresponds to one group. So there are two generators we denote as J plus and J minus. 3 plus and 3 minus. Actually, they are vectors. Corresponding to this two. And the 3D rotation, physical rotation, 3D rotation generated with the delta down with minus. And this is by physical in the original 3D rotation as a sub algebra in this SO1 comes 3, okay, which is this one. So we introduce spinner as a particular representation. So you know as what happens if we only take half of this as non-trivial representation, say half zeros, comma zero, or 0, half. And this we call the spin half representation. And the spinner is essentially the object, so-called spinner is the object active by these representations. Okay, and we also put another name for this, and for this one, we call this is the left-handed. Okay. Left-handed, and this is the right hand. Okay. Naively, you can think why, because we only have left, right. This is right and not left. Okay. And there's a physical reason for this. We're going to discuss this left or right, left-handedly, right-handedly today in great detail, because we think that this is the chirality of this spinner. Okay, something called a chirality of the spinner. It's basically related to this decomposition. Okay. So in the original physics space, because of this decomposition, you can think about any representation consisting of the left mode and the right mode. Okay. So chirality comes from here. Yeah, we're continuing to discuss this left-handed or right-handed today. So last time we also made this representation. The generators act on this representation quite clear. In particular, we identified this J minus in terms of half sigma. Okay? And the sigma is the solving matrix. Okay. So we're familiar in quantum mechanics in understanding this SU2 or SO3 rotation. So there's a realization, very familiar realization generated. So for this one, this is a half sigma or minus, and for the other is a plus identified with the half sigma. Right? So if you know this one, we can write down the Lorentz transformation. Okay, we call this this kind of spinner, so left-handed spinner. So left is transformed. In this way, the right transform in this way with a plus sign. Okay, okay. Okay. It's essentially says the Lorentz transformation is also decomposed. Okay. The left transformed by itself, and the right transformed by itself. Okay. It also decomposed. You can also view this as a representation is a reducible representation. Okay, you see, the reducible representation by definition, right? Reducible representation means there's a subset of objects that just transform among themselves. Okay. We intend mentioned if we combine this left and the right together, one can form something called the Dirac spinor. Okay? And clearly, Dirac spinor is a more carries more components. Usually, we write as left and right in this way. Right this way, because we start from wire spinor. Okay, we start from wire spinor essentially. And then we combine them to form. And we also introduced some notation called the psi bar, which equals to psi r dagger. That L dagger. Okay. If you employ this notation with some 4x4 matrix or the gamma matrix, this way, and the sigma is sigma bar is the 4-component sigma matrix, okay? Or with a vector with the component as sigma matrix. Then one can get the nice form of to describe the Fermions. For example, one can get a nice form of Lagrange. In this way, or there's some shorthand notation, I can write even some slash. Okay, this is some slash. Slash means that with the gamma mu in front. Okay, with some operator. So this is called the Dirac. Okay, so we find the work that the equation motion. View this the psi bar and psi I independent. I wish with respect to psi bar and get equation motion for psi. Like this one, okay? So notably, this is a first order differential equation. Okay, first order differential equation. Okay, then you may get with the target, like how this connected to how this is related to Klein Gordon. But because of this object, it has several components. Okay, this is the couple. This is the coupled first order differential equation. Okay. If you decouple it, you can see the second order in terms of component. This is what's going on. So we are going to continue the discussion of the Chirality equation with spinors. So we mentioned the gamma matrix can can be constructed using this sigma. Okay. We also know this sigma are the generators. Sigma are the generators for the Lorentz transformation, right? Sigma are the generators for Lorentz transformation. Okay. Sigma is essentially J minus J plus. We know J minus and J plus. We could go back to original. All the generators of Lorentz transformation. J plus J minus comes from there. You compose Lorentz group. So this means what? This means if you combine them into another form, there must be a formula for the Lorentz generators using this gamma mu, right? You see? The gamma mu is the sigma. So what is that? So Lorentz generators in terms of can be written in terms of gamma. In terms of gamma. Which is the sigma mu nu equal to I divided by 4 commutator gamma mu and gamma nu. Okay, you can check it. Okay, you can check it because we know how Lorentz generator should be expressed in terms of sigma. And gamma is defined as sigma. Okay, then you can check this is the form for generator in terms of gamma itself. Okay, and you can also check there is a algebraic relation if we use this form, okay? Which is the translation of S mu nu, the component of this S, okay? Okay. By this, I really mean I don't mean some matrix commutator in terms of this index, no. I really specify this mu nu rho sigma, okay? So because for the specified mu nu and rho sigma, this is already a matrix, okay? Is that clear? Because when you specify mu nu, you specify here mu nu, right? Right? So this is the commutator. Each gamma with the specified index is already a matrix, okay? So by this commutator, I mean that commutator for that matrix, okay? We can work it out. Right. G Look at this one. This is just you can straightforward check it. This is true. And what is this? Looks familiar. What is this? This is Lorentz algebra, right? This is Lorentz algebra. This is nothing but Lorentz algebra. This is Lorentz algebra. Okay. This is the Lorentz algebra. So we found another realization for the Lorentz generators. Indeed, satisfy the Lorentz algebra. Previously, already mentioned it. We used the vector representation. Okay, we found. Remember that we used vector representation. It means that the Lorentz vector in terms of this vector space, how to write down the generators, right? Previously, we have some lambda, capital lambda. And then here we obtain the same algebra in terms of another realization, okay, for the Lorentz generators, okay. this is the form in this spinner space. You see, so in spinners, not a vector space, we have another form of the generators. Okay? You might think, are they equivalent? They are not. They're not the same. Okay, even though they satisfy the same logic. Okay, but they're different. Why? Because they stay in the different representation. Okay. Okay. Previously we have half, but here we have half zero and zero half. Okay. These are the different representations. Okay. One is the vector representation, other is the spinner. You can check yourself. Indeed, they are different representation, even though the dimension is the same. Okay. Doesn't matter. You see, here dimension is 4. Previously, the vector case dimension is also 4. But even though the dimension is the same, these two representations are different. Therefore, the generators express in different form. Okay? But they do satisfy the same logic. And we can also work to specify, to mention, to emphasize the this relation. This relation is independent of the representation. Last time we mentioned this is a particular form of gamma matrix. You see why? Because we do from wire basis. We start from wire spinner. We construct this gamma. Okay. But you shouldn't think this is the only representation for the gamma matrix. Okay. Okay. The true intrinsic definition for gamma matrix is, as we mentioned last time, the gamma mu anti-communicate with the gamma should be equal to 2 mu nu. Okay, this is the intrinsic definition of the gamma matrix. Okay, so there are infinite many different representations of gamma matrix. That's the only one. Oh, in fact, only use this one. You can show this is true. Okay. Okay, therefore it's very consistent. Why? We use the intrinsic definition of gamma matrix as the input. You can show Lorentz algebra is satisfied. Okay. It does not depend on any particular representation of gamma matrix. Okay, because there are many different forms of gamma matrix. So in terms of this, one can also write down the Lorentz transformation to lambda as denoted as a spinner, lambda spinner, because I theta mu nu as before, as we ran before. Previously we write some theta v, right? V mu nu, right? You generate to form a very big matrix. We call it V mu nu. We write the Lorentz transformation in terms of e to the I theta V mu nu. But in this case, it will be I theta F. Okay. This is the transformation matrix for the spinners. Okay. So of course, another very important thing is how can we find the Lorentz invariant object? Okay, Lorentz invariant object. We discussed last time for some examples. Okay, but in general, it's not quite clear yet. So last time we discussed some particular combination. For example, this one psi L dagger psi plus psi R dagger psi L. Okay. We discussed this kind of thing, and we justified that this is Lorentz invariant. This is Lorentz invariant. This means what? We use this new notation, 4-component notation. This means the psi bar psi is Lorentz invariant. but not side dagger side. Okay, this is very important. If naively, you might think that this kind of thing, right? But we already ruled out. This is not Lorentz invariant. This is Lorentz invariant. So here we just defined. You can think of this is definition. We define the set bar in this way. If you want to write the set bar in terms of 4x4 matrix form, set bar is not quite side dagger, but side dagger times some gamma 0. Okay. With gamma 0. Okay. So side bar is defined in terms of 4 spinors. This is side dagger times gamma 0 because it's not side dagger itself. Okay. This is side bar. You can check only in this way, consistent with that definition. Okay. Okay. Because gamma 0 does the job to exchange these two. Okay. You see. Because naively, if you only take a dagger, you might get the side L dagger, side R dagger, right? Then if you use that object put together with side, you don't get this one, okay? Rather, you get L, L, or R, R, okay? And that is not Lorentz invariant, okay? As we just defined last time. Only this is Lorentz invariant, okay? So this is a specialty about this 4 spinor. And now there are many tools, right? You can check many consistency between what we claim. Okay, for example, we already know Lorentz transformation in terms of the 4 spinors or gamma mu, okay, or gamma matrix or Dirac matrix. Okay, so you can directly check all these relations in the 4 spinor base. Okay. No, you don't need to go back to the wire spinor, even though we call 4 spinor on the wire spinor. Okay, so you can check everything standing in the 4 spinor base. For example, you can check why in the 4 spinor space why this is the Lorentz invariant. Okay, last time we justified in this one, we see the Lorentz invariant, but now you can directly do in the 4 spinor space. You can check again. You can check under Lorentz transformation the side bar side, which is the side dagger 0 side, we will transform. Okay. How it transform? Because we know side transformed under this. Side transformed under this one, right? Right? This is the transformation matrix for side. It's a 4x4 matrix, okay? It's a 4x4 matrix. So we're transformed side transformed to lambda s psi. So side dagger will become side dagger lambda dagger. Okay. And then there is a gamma 0 psi. Okay. And you can show this is nothing but side dagger gamma 0 psi as inverse. Okay. Lambda as inverse lambda as psi. Okay. In particular, this equals to this. That's right. You can in particular this equals to this, and then we got this answer. Okay. We got psi. There it goes. Okay. So we just Lorentz invariant. Okay. Just Lorentz invariant. Right. So there are many interesting exercises like this. Okay, you can check yourself. All about this gamma matrix. Okay, the lot of relations among these different combinations of gamma matrix. Right. Okay, here you can show this because everything in terms of gamma matrix. You see, because this Lorentz transformation is already expressed in terms of gamma matrix, right? With the exponential, right? And then all these are just the gamma matrix. So essentially, all these exercise about to deal with impute a different object in terms of gamma matrix, right? Right? You can check a lot of relations. This is one example. Just one. Okay. So later, when we compute the amplitude in the real QED, which involves spinors, we quite often we also evolves. We're going to use some trace relations. There are also many interesting trace relations. Because gamma matrix is a square matrix. You can take trace. You can multiply many different gamma matrices and then take trace. Okay. Okay. And if there is a trace, we know there is also cyclic relation, right? So you can between this gamma, because of this gamma matrix is a very special object. So you can derive many different relations. So what about the others? So all the other. So we won't get some feeling, right? Which kind of object can be treated as the Lorentz invariant or Lorentz covariant? Okay. Indeed, we want some feeling. Get some feeling. So what about other Lorentz invariant? Or covariant? So one can check with this side by side. We already justified this is the Lorentz invariant. Then one can insert. This we already saw last time actually. We already saw from this mark. It's Lagrange, right? This is this kind of object transform actually the Lorentz vector. Okay. So with the side by side, insert some gamma mu, then the object looks like a Lorentz vector. You see, like you see they carry a mu index, right? Right? That's the point. Carry a mu index. Now you ask me why you put the gamma matrix in the middle, not in the other one. That's for the good reason, right? You see it, right? Because this is only this kind of combination you can form. You finally get a number, right? Right? Because this is the column. This is the column. This is a row, and there's a matrix in between. Okay, right? So this is a brief notation. You should really keep in mind always. This object has 4 components. Okay, okay. This also has a 4 component, but with a transpose. And this is a 4x4 matrix for each mu. Okay, mu can run, but for each mu is already a 4x4 matrix. Okay, so putting them together, let's first specify mu. Say mu equals 0, 1, 2, 3. For each specified mu indexes, you should view these 3 objects and put them together. There's already a matrix product. Okay, in the spinor indexes. Okay, because they have a spinor component. So this is a good reason you should write in this way, right? You should write in this way. Okay, you should write in. And if you want to create some tensor, okay, then you should insert more. For example, you should the sidebar, insert once, and again, the gamma mu and the gamma mu. And you can check, this looks like a Lorentz tensor. Because different index, mu and mu. Of course, I skipped how to prove it. This is a really interesting exercise. You should do it. You can show it, because I already tell you how the spinor transform. In particular, in principle, I don't need to tell you how gamma matrix transform, okay? Because obvious you can check. Because transformation matrix is already in terms of gamma matrix, and the only thing you need to check is the play with this matrix product for the gamma matrix. And so you can check everything okay? Here. And of course, we also store from this direction of Lagrangian. We can also insert a derivative. Some object like this also transform like Lorentz vector. Okay. Lorentz vector. Okay. So these are transform. This object transform. Like tensors. Like Lorentz tensors. Okay. So this is how the spinners or Dirac spinners or their combinations, how they transform Lorentz transformation. So do you have any question about the transformation property of the spinners? Okay. So let's discuss. We already introduced this Lagrangian, and I guess many of you already know this Lagrangian describes our real world electron. Okay. So this is an extremely important theory to describe our real world. Okay. So of course, our real world there's also photons. So we should discuss how to couple this fermion to photon. Okay. How can we couple this electron? So very luckily, even though spinner has some internal structure, right? Many components. Sometimes it's a little scary. But very fortunately, if you want to talk about the coupling to photon, really very much like a scalar. Okay. Okay. In other words, the coupling piece to photon is very easy. It's very simple. Okay. Very simple. So how can we see it? We can say this one. So for a spinner, so even though the spinner transform looks complicated under Lorentz transformation, but under gauge transformation, or if we want to talk about the gauge transformation, it's very easy. Okay, and as always, we discuss gauge transformation. Starting point is some global transformation, but then we gauge it. Okay, then by demanding gauge invariance, you can form some theory. The gauge invariance is very important, and so we start from a global transformation. So for a spinner with charge -1, the global transformation is very simple. It's precisely the same as the scalar. Okay? It's just the global phase. You rotate by a global phase for all your components. For all your components. Whenever I write something like this, here is a number. Okay? Then you should understand that this really means whatever inner structure contained in this side should transform uniform. Okay? So everybody does the same job. Okay, does the same transformation. Okay? So this is what this means. Okay? So everybody rotation by your phase, and you can check that indeed by our criteria to define some global symmetry, this is indeed an invariant under that phase rotation. You see, right? Right. So under that transformation, this Lagrangian is indeed invariant. So this is invariant. Yeah. And as what we did for together, like the same, we want to promote this to a group transformation. Meaning that we promote alpha group alpha as a local function, the function of the space-time coordinate. Right? If you do this, then story becomes a little complicated, and by demanding the gauge invariance, you can try to constrain the theory. And in practice, we should first discuss how to promote and improve the Euro derivative. The Euro derivative is partial mu, because we have a partial mu like here, right? So we promote this through a covariant derivative by adding IE a mu term, or this new derivative is covariant derivative. That's very much like what we need for skeleton. So the difference here is you can see because derivative, as emphasized, only appears in the Lagrangian once, not twice. Okay, not twice. So there's a difference. So the improved Lagrangian L will become the time for I only once covariant derivative minus m line. Okay. And okay, this is the improved Lagrangian, and also the improved equation of motion. This is the improved one. This is meaning coupling to photon. Okay. At this moment, we didn't touch the dynamics of the photon. We didn't talk about. We can, but here we just try to first couple it to photon. Okay. We didn't include the Maxwell Lagrange, meaning you can think at this moment the photon is the background. Okay, it's not a dynamic. But even here you can see something interesting from the equation of motion by treating photon as a background from here. Okay, from here. We mentioned last time, or we mentioned somewhere. Okay. From the Dirac equation, we can actually recover the Klein-Gordon equation. Okay, right? Because this is the operator acting on this object, right? And this is equal to 0, right? So you can multiply some other operators from left. Okay. Okay. Does not change the equation, right? Should still get 0, right? Because this is 0. So if you multiply some I partial slice plus m, okay, from left, you can see you get precisely the Klein-Gordon equation, okay, from here. Okay, and then now we couple it to photon, improve this ordinary derivative to this covariant derivative. So we can do the same exercise. Namely, one can check this equation. They're true, of course. And if we multiply this equation from left by some other operator, you see? So you can get the equation looks like this. Okay. As said, if this d is if there's no a mu, it's only the partial mu. This is nothing but the Klein-Gordon equation. You can check it, right? In fact, okay. Or this is equivalent to say, by multiplying this new operator, you get Klein-Gordon equation. Essentially means you decouple your original coupled first order equation. You get second order. Right? You get second order. It's interesting. It's an interesting exercise. You can check yourself. This tells you how to recover a Klein-Gordon equation from a Dirac equation. Nice. Now we want to emphasize such some equation looks like this. There's a new background photon. Okay. There's a new background photon. in this equation. So what do we get? You calculate this equation. You get something interesting. Okay, so this equation is nothing but there is a this operator looks like this one, will equal to 0, and this is nothing but let me write this explicitly. This is some equation looks like this. So it's like this, okay? So eventually you obtain that the equation looks like this. In particular, it gets a new term. This new term does not appear in the case of scalar. Not only appear in the case of fermion. Okay. This is this term. What is sigma mu? Sigma mu is what I defined definition. Yeah, sigma mu is basically the commutator of gamma mu and gamma nu. Sigma mu is proportional to this up to coefficient. That's the definition of sigma mu. So the point is this new term. This new term tells you some new feature about this fermion compared with the scalar. Okay, previously we claimed that from there you can recover the precisely Klein-Gordon equation. Then you might say, think, okay, since I can got the Klein-Gordon equation of motion from the Dirac equation of motion, okay? So you might say, okay, Dirac fermion is nothing but some rewriting of the previous scalar, okay? Or take some square root of the equation of motion of Klein-Gordon equation. But that's not true. Okay? I'm telling you using this example. When you couple with photon, you can see clearly. Not only that, there's some more structure coming from the fermion, okay? But in order to see it, you have to couple with photon, okay? That's the point here. Precisely because of these new terms. Okay? Because it's new term. Is that clear? This new term. So this new term, you can see, if I have a photon as a background, then I could have a non-trivial F mu, right? So what is F mu? F mu is the B or E field, right? Right? Which means if you have a non-trivial B or E field, you can measure something coming from this coupling term, right? Because this term appears in the equation of motion of the fermion. Okay, it contributes the equation of motion. It's a factor the equation of motion of fermion. Okay, and sigma mu is something related to the spin for sure, right? Of the fermion, right? The sigma mu is defined using the commutator of the gamma matrix. Okay. So this term means if you have, for example, if you have a non-trivial magnetic field as your background field, then there is a non-trivial effect. Okay. So this coupling indeed, from experiment, people already verified the contribution coming from this term. Okay. So this is called the magnetic moment of electron. Okay. Which is the famous property of the electron.
Sorry, what's the definition of sigma mu?
Okay, I understand. So you do magnetic moment. Yeah. Let me find the sigma mu. Somehow I didn't include the definition here. Only 1 minute. Yeah, sigma mu is the commutator of the gamma matrix. Okay. So, yeah, it's this one. Okay, it's this one. Okay. And maybe up to some numerical coefficient, you can check yourself. Okay. That's the sigma mu. Yes.
The partial in the last form is the normal partial or the D?
It's not, because I want to, yeah. For sure, it's not only the normal partial, it's covariant partial. But the point is, there's a new term. Compared with scalar, in the case of scalar, there's also covariant. So I'm telling you, this square is really go beyond the scalar case. Okay. So do you have any other questions? Okay. So the next of course, which we'll touch or continue to cover is the Lerner's current. Okay, and for Lerner's current, this is the simpler than the scalar case. So Lerner's current. The current for this one is really only need a global symmetry. That U1 symmetry. It's global U1 symmetry. So in this case, you can check whether the current is simply the psi bar gamma mu psi. Okay, mu psi. This is whether the current. Okay. It's somehow consistent with the thing earlier. This kind of combination is a good Lorentz vector, right? Because we know J mu is a good Lorentz vector. Yeah. Because J mu is the physical current. It's good Lorentz vector. And different from the scalar case, there's no A in this J. There's no A field included in this J. Okay. And you can also say, if you want to, for example, try to construct the conserved charge using this zero component of this J, then you first pick up what is J0, right? So what is J0? Then you realize the J0 is nothing but psi bar J0 psi. What is this? What is this? Okay, can you see what is this? Yeah, this is nothing but psi dagger psi. Okay. This is nothing but psi dagger psi. Why? Because gamma 0 squared is 1. Okay? So this is the psi dagger psi. So this explains why psi dagger psi, from the top point of view, why psi dagger psi is not a good Lorentz vector, right? Because it's only a component of some vector. It's a component of vector, cannot be treated as a vector. It's only a component. So there's no a mu term in the current. Compare with the together. So this is the real inner QED, or is the real world QED, and you can see by this J mu, the coupling once you couple with this photon, the coupling is indeed given by A mu G mu. Okay. And in the case of scalar, I believe maybe several weeks ago, we made some statement which is incorrect. So in the case of scalar, because J do have there's a mu term included J. So when you see the, for example, from Maxwell equation point of view, you see the partial mu F mu nu equals to J nu. Okay. You see from here, the conservation from the left will lead to the conservation from the right hand. So partial mu equals to there. See? Okay. Right? But this is only true when J does not contain A, right? You see? If J contains A, you need to do further variation with respect to A from this J, okay? See? If J does not include A, you simply get this equation. Okay? If J contains A in the case of together, what you should get is maybe some J tutor, which is not really the current J tutor, A. And then you do the variation with respect to A nu. Okay? This is what you get from the right. Okay? So in the case of scalar, it is this J tutor A coupling. The conserved current is really this one. So if J does not include A, it's simply this J is simply the conserved current. Okay? But in this case, everything is more simple. Everything is simpler than case of scalar. The J does not have A, and in the Lagrangian coupling is A mu J mu, and J mu is simultaneously the conserved J. Okay? Do you have any question about this real or QED? What is the conserved current? So then, so let's spend some time to discuss the chiral nature of this Fermi. Okay, we mentioned there's something called chirality. Okay, but this is also very, very important. Okay, if you aim to do some research, yeah, you should pay attention. Something called chirality. Thank you. So as we saw in the wire-based gamma matrix, let me write it again. I'll write it here, right? Gamma matrix. We saw in the wire-based, the expression of the gamma matrix is this one, okay? Is this one. And the spinner left and right, they transform individually. So we define the chirality because of this. So it seems that there is a reducible property. So left transform among themselves and the right transform among themselves. So we classify these two groups like we put the name chirality, or we define the left handedness and right handedness as the chirality. Okay. What do you mean by chirality? What do you mean by the chiral property of this fermion? So it's defined this way: the left or right handedness of a spinner is called as this chirality. Okay. But as we talked about already for Lorentz transformation, we want to understand this property from the four spinner point of view. Okay. We don't want just understand it from the wire basis or from two spinner and then four spinner. Now, since we already arrived at the four spinner notation, four spinner language, right? We want to understand everything from the four spinner point of view. Then the question will be, if you give me an arbitrary four Dirac spinner, can I find what is the left or right? Right? That's the question, right? In particular, as we know, gamma matrix is the representation is not unique at all. Okay. There are many different representations, right? For some reason, someone sent you some four spinner in some basis he likes. Okay. So how can I find what is the left part, what is the right part? That's the question, right? So in other words, we want to talk about this property in a more general level. We don't want to only discuss it in some particular base, okay, or some particular representation of gamma matrix. Okay. Okay. We want to discuss this property from top point of view. So then to answer that question, we should develop some trick or techniques. So indeed, you can do it. Okay, you can do it. Only if, indeed, for any given four spinner, we can project. If you want to have some left part only, then I can project out the right part. Okay. If you want to have right, maintain only right, I can project out the left. Okay. Okay. This projection can be systematically done. Okay. Does not depend on which base you're working. Okay. Does it make sense? Okay, let me make this more clear. So you might like this some very, very explicit form, right? So you see upper half is left and the lower half is right. But I should alarm you, okay? There's a caution here. You shouldn't take this as too serious, okay? Because this nice structure only happens in some particular representation of gamma matrix, okay? In general, they could mix, okay? In general, they could mix, okay? For example, you have four components, right? In some cases, maybe the first and third, okay, belongs to the left, and the second and the fourth belongs to the right. It can happen, okay? Because you can change your base, you can change your representation of gamma matrix. Then your spinner will be then switched to this or that. They mix, all the components they mix up, okay? Will not be so nice, okay? In some general base, this is the upper half is left and the lower half is right. For that reason, but we do know physically, four spinner should contain the left part and the right part. Then where can we see it? Okay, if we want to systematically see it, that's the thing we want to discuss. Okay, so one can try to project that. One can try to project out left or right. Okay. From a given rocks. Okay. So for that reason, we introduced some new object called gamma 5. Okay, gamma 5 matrix. What is gamma 5? Gamma 5 is defined as I times gamma 0, 1, 2, 3. Okay, see, very nice. Okay. So we already have 0, 1, 2, 3, right? Just put them together. Put them together with the I in front. You get gamma 5. Okay. Now, to see it explicitly, it's good to write it in some particular base. Let's say wire base. Right? Because in different base, gamma matrix has different form. So in the wire base, a wire representation of the gamma matrix or spinner, you can check gamma 5 is nothing but minus 1, 1. Okay, minus 1, 1. And this one, each one is a 2 by 2 matrix. Okay, it's a very nice matrix. So because of this, you can easily find again in this base, if you act gamma 5 onto this false spinner, because in this base we do know the false spinner organized in this nice way. Okay. Okay. If you try to act this, what do you get? What do you get? Of course, you for the left, you get a minus sign, right? For the top, you get a plus 1. Okay, this is what you get, right? Because you have minus 1 here, 1 here. This is what you get. So we see clearly gamma 5 for left, gamma 5 has an eigenvalue minus 1. For right, gamma 5 has a plus 1 eigenvalue, right? For this reason, we can easily using gamma 5 to construct some projector. Okay, the projector can project out either left or right. Only the other remain. So this means the left or right spinors are eigenstates. Of gamma 5, okay, with the eigenvalue of plus or minus 1. Sorry, minus plus. Minus plus, okay. Okay. So the logic, let me repeat the logic again. Logic is, again, up to here, we want to make every statement or discussion in a general way. Does not depend on the representation, right? But in order to understand how it works, okay, we always want to see something explicit, okay? In order to understand how it works, we try to write down everything explicitly in terms of some particular base, okay? For example, in wire base, you can see, so up to here, we justify in wire base in particular, indeed, the gamma 5 can start the job because gamma 5 has the left and the right part. That is why eigenstates, okay? But you should keep in mind the property of gamma 5, okay, does not depend on some particular base. That's the point. Because of the property of the gamma 5, so one can construct or one can define projectors. Let's say we can construct a PR. Okay, PR means the project out the others, but not R. Okay, that's PR. So PR will be 1 plus gamma phi over 2. Right? And this is nothing but a 0, 1 matrix. Okay? 1 really means 2 by 2. Okay. So if you act this one for a given force spinner, and you can see clearly because there's a 0 here, right? The upper half is thrown away, is projected out. Only the lower half is there. You see? Because of this matrix. And also PL is 1 minus gamma phi over 2, which is the 1, 2 by 2, 0 here. Okay? So that why we want to some funny object looks like this, because we really want to act a PR for a given force spinner object. I get only the lower half, which is the right hand side. Right handed is half. Okay. Now let me emphasize it again. Last point, the projectors. The definition of the projector, 1 plus minus gamma phi over 2, is phase independent. Meaning that even though in terms of explicit form, we need to try to work in some way, but the projector, meaning that the definition of the projector using this compound in this way, can always does the job to project out the left or right. Okay, this statement is independent of the base. Okay? Why? Because I don't need the particular base. I can discuss all this right without the particular base. Why? Because the gamma phi is defined this way. I can talk about it very abstractly if you use some matrix defined in this way. I times gamma 0, 1, 2, and 3. Disregard any particular base. Then you can always use this one. Using 1 plus minus this gamma phi over 2 to act on some for any arbitrary given force spinner. You can project out. That statement is independent of a particular base. Okay? So it looks very nice, right? For example, you can just switch to some other base, right? You can check it. Then you can realize that in some not very nice base, this left or right may be mixed, right? Not only the upper half. You can see. 我们休息一下，休息15分钟。
你要说难以为我就是它这伽马0、伽马1、伽马2、伽马3不都是对嘛？好，硬要说的话，就是它相当于它把这个伽马0那个就是它把这个1，然后伽马就是这个嘛负这个这个嘛 x 负这个嘛 x， 那你伽马5这个长对啊，那它问题一面是它是非常非常的1减伽马5，那最后不就是一个给定的矩阵？这里设定那个伽马可以加伽马在这里我可能这个我不知道， 但是伽马五它也是个不是换动手，放进去打，这是给的，你
本身给药的，
然后也
不是这个真打
对，上另外两种。我觉得可以
啊，对，你要
不是长月还有自己这个高血跟叶灵回血自换，
但是你
这伽马五它
但是你要把它放进2个人这的，
你如果换一个杯子的话，
对啊，
那伽马零伽马
这个手让那
个
我觉得巴拉巴拉搞烂了，这个
那这个这样，
牙可能
就是知道来说，但
然后不该那个谁
然后把它变成
我觉得我才就是说实话，但我没打，我
我再把它那个做的
那个
是
你那个放什么叫800个那个
那完全了。
马群呢，他是不是2个项目的出去？
不是要给我看，是这个他这个不是5AC 都不带的，
对，
这是相当于这些。
然后
马群那就是2个项目完全不同。
啊不，我原来用的是直接用的
他的自己的赛，
没有伽马是跟狄拉克把它组成了一个4乘4，
所以
我们能用814码出来。
刚刚5觉得应该可以吧？
他是在上面带
啊不，因为它这边的伽马5跟表象无关，
这个是
伽马0、伽马1、伽马3、好像可以说没有关系。它的代数性质，它作用在这个范上产生一些性质是和表象。伽马可以取到，它可以取到马拉纳，
比如说我上个东西来讲。
那你伽马但马拉纳它也是这4个产生的情况，它长得就真的形细胞不一样，但是它的作用是
我有个印象，
对，就是
哦，还有人拿它跟肩膀上的那个伽马五
意味着我的伽马1
这个好像见过，
比较不太恰当的。
我起床，就比如说你我太别被删，
所谓的表象的我知道了一个我去同意。
哦，那就是
合同方案就是我这个伽马在这样做。
他一分可能对角牙齿高明，他所单位是加强和或者相比
这个在另外边就是伽马0和伽马0的它依旧
就这样。
伽马5的形式是不变的，伽马5可能会变成什么01、什么228。
伽马5跟马九那
它期末考试它就是会把这个第二个质量硬成
好像
是这样
啊，对，
这个吧，
马上你不能这样想，
它是个变化，
对
不讲的是，马上了是带 constraint 的它是个变化
啊，
不是这个 derive， 那个还是 constraint 上面会加上有约束的。马九那它是没有814，
真有办法，
可以，我们会讲，下面就会讲。
真有
他的 file 是不是不能写在上面？
哎呦，
但不行，是另外一个。
我不知道。
让我来看，当时是给我的，当时看一下啊。
马上来写成赛就叫赛 L， 然后还有伽马2乘以赛 L star 下面，只要么左，然后以后它就变成左边和右边是
我觉得马云它是2个相同。
啊，就是
可以。好，3号你可以这样用，它是只对一部分属性，没有既有组合。
那这里它的这个手性能和就是物理上它运动方向和这个
当然肯定会讲，
没事，应该是
就是马斯利斯看得到，
对，它是应该是手。
我只是写成了啊的写成，
它是左手和右手，
别人自己看。
这实际上是物理上为什么叫左手？它是马斯利斯 particle 就可以看出来，它是 particle 的运动方程标准干。
我还是没吃饭。
两本上就是说，
它 choose frame
让那个
动量
叫什么？
它零指向嘛
，OK，它相当于这个负1
动量指向是
应该不是吧？
上分别各有2。
20
看着自己动量方向看，
20%，
做一个Helicity，它要么是正，要么是负。
啊，
就这个Helicity就是你固定的运动方向，就它有一个转嘛。
120不能贴，是的，
对，
它其实最主要的，他们比亚克把它们整合了一下。那你就相当于给它那个限定空间换了一个，限定空间换了一主机嘛。
对，然后加入动作之后，那整个它就在动
还是那个吗？还是它定义变量？
不还是那个。
那个右边右下角那个是什么？
就是那种
对，
你说今天还有一个那个它跟小野寺，
它是定义还是什么？哦，这个定义跟它本质还是我的意思就是，F 是它是作为那个，它是有没有 A 减去这个定义，这个它上面那问一下，
啊，是那个它是
你还记得上次课吗？我跟你讲这个。
我知道，就是它的定义是它最后
Consistency of the electrical field is equivalent to the conservation of another current。这怎么解释呢？当我们推导Maxwell方程的时候，如果有一个外源项，
对
which is given by J tutor，coupling 是 A J tutor，所以我在推导 A 的运动方程的时候，显然要对 J tutor A 进行变分。是，
对对对。
我们假设 J tutor 里面没有 develop， 只有 A，
当时
那就需要对 A
关系是成立的，对。但当时是通过 F 引进，然后再输出了 J， 然后这个关系是一个成立的关系。当时不是 F 有对吧？
这是构造，
这是构造的嘛？这不是错的。
我们传的 C， 整个右边的整体，最后面求导完了之后，它才是 conserved 的 definition。我们 check 这个 conservation 和 consistent condition 就从这个方程。你在左边再做一个 partial mu 看出来那个。
那这 F 等于那个 partial mu。
对，我想咱们 explain。把 J tutor A 放一起之后，对 A 求导或者求变分之后得出来的结果才是真正的 conserved 的东西。不一定等于这个 J tutor 自己，要看 J tutor 到底有没有 A。
这个东西是F 还有没有一定是partial mu A 有减去 partial。
你再说一遍 F
我
第二个是。
就那个定义，这个也算是它的定义吧。
这谁的定义？
这个算是定义了一个 F U。
No，
这不算，
这个是一个方程。
一个方程。
这个告诉你 F U 跟 source 的关系。
哦。这是个方程，不来的。
我最看到多少视觉效果。但是我一年的话没看上去掉下来。 什么问题？喂，
我这觉得人情吧。
因为我们现在不是可以纠缠，是不是守恒点啊？我不知道可以纠缠，是不是守恒点？我就想跟你说
啊，那为什么一定是守恒流程？
不是守恒点，因为它我不知道是啥。
啊，就是，但是我们需要一个矢量。
我先看它。
我的理解是我们需要一个矢量，然后把它和另外一个矢量变成一个parameter。
假设这个
还没开始开发，反正就一个。
不能 T
还有一个两个人。
这个未必是守恒。但是我对它求 A，
哦，要求它是守恒。
然后我右边就是这个嘛。
对。
那能推出来，那说明。
哎，我以为它只有一张，
然后我这个感觉蛮强的。
但它下面这个架构，
这个边就等于这样。丢它没有，它未必是红。如果它里面有这个的话，因为它也是个 A 的，
开发路线。哦，现在才做了基础给它写。
这个其实是
因为你一开始不知道 A 里面有和它 A。
哦，对对对。
你就先假设它还是
跳这个地方。
当然就是这种。
所以它一个
对，他们比如讲到你们尝试。
他们追求，这是这里头，手我都是对的，不去了。将来冲突的一个对象是改变一个，
守恒流是
不一定推出来，这有的发球人，这个守恒，这应该这样。
Okay, let's continue. So we saw this chirality of the false spinors. Let's see it by using this amplifier matrix for projectors. And let's talk about all. We want to see this property and the level of equation motion. Level of equation motion, again, to write down everything explicitly, we choose the wire phase first. Quite often, some conclusions is phase independent. That's always the crucial point. Now, equation motion, I write in wire phase explicitly. You can write it this way. Okay. We know equation motion is nothing but the I partial slash, okay, minus m acting on the four Fermions, 4 spinors. Now I write it explicitly using the matrix, okay? It's building block again 2 by 2 matrix, and then this will be the explicit form of the equation motion. See it, right? This is the equation motion. I write everything explicit. And in P space, I can replace the derivative by the momentum P. So this equation, clearly this equation also means there are 2 component equations, right? 2 component equations. First equation is given by this act on this equals 0. Secondary given by this act on this equals 0. Right? There are two component equations. So I switch to the momentum space. The component equation is nothing but sigma mu e mu act on psi r. This act on, I replace I partial mu by a p mu, right? So this is sigma mu p mu. Okay, so I switch to momentum space. This act on the psi r, as you can see, this is nothing but, further I write this explicitly. This is nothing but energy minus sigma vector plot, the basic P. Okay, it's nothing but this one. Okay, I write this mu index explicitly. Okay, the energy, this is the true momentum, plot with this sigma vector, Pauli matrix vector, and act on the psi r. And this is what? This is the given by, this is the first equation, right? Given by the mass times the left component, right? This is the first equation. And the second equation will be the sigma r mu p mu act on the left, which by definition is the energy plus sigma vector dot p physical momentum act on the left part equal to mass times the right. See? It's very symmetric, right? You know this, right? These are the component two equations from there, okay? Same equation. So as we emphasized in the very beginning, because we start from the wire spinors, we know this is very clear. We noticed in the very beginning, the non-trivial mass essentially mixed left and right, right? You see it from here, right? So if mass is 0, then left and right completely decoupled in the level of equation motion, you see it? But if mass is non-zero, they mixed, okay? This is the physical reason why we need a 4 spinor to describe our electron, not 2, okay? So suppose if our electron is massless, then textbook will be rewritten in terms of all the important spinors will be 2 components, not 4 components, okay? Okay? But mass is not 0, so they mix. You actually need 4 components. But we do, as a theoretical discussion, we do want to find the specialty about the massless fermion, right? So for massless fermion, meaning m equals 0, the equation of motion is simplified further. See? So if m equals 0, from there, you can see the equation of motion even simplified. I can organize the equation of motion in a very, very simple way. For example, for the first, I get some equation looks like this, right? You see it? Why? Because this is energy, you see, right? Dispersion relation relate the energy and the log of the P, momentum, right? For massless particles, okay? So I guess the equation looks like this. Because m is 0, okay? The mixing is gone, okay? There's no mixing. So left is left, right is right, okay? And also for the left part, if this operator acts on the left, I'll get a minus left. You see? So this is for massless. So for massless fermion, the equation of motion can be written this way. Okay. Because of this form suggests combined with massless condition and the chirality, okay? There's some new operator you can define, or some new physical quantity you can define, right? You see, I can define this operator to measure some physical quantity, right, for the massless fermion, right? For example, I can, yeah, that's essentially what we want to discuss further. One can define the operator here as something called helicity. Helicity operator. The helicity operator is defined in this way. Sometimes we denote it in H hat, use helicity. And these operators will use hat. The helicity operator is defined in this. Okay? So what's the physical meaning of this helicity operator? Can anyone say some physical meaning of this object? Hmm?
Angle between the spin direction and the direction of the movement.
That's right. So to answer the physical meaning of this H hat, we have to first answer the physical meaning of this sigma hat. Okay, sigma vector. Okay, so what is sigma vector? Sigma vector is essentially the spin operator, right? What you learn in your quantum mechanics, right? Sigma vector is the spin operator. We know spin is a vector operator, okay? There are some directions, right? That's the spin operator. So if you know this is the spin operator, then you can easily understand the meaning of this combination. This means what? This means that if my particle is moving in this p direction, okay? Okay? this operator measures the overlap or the inner product between the spin operator and the motion direction, right? Right? This motion direction, and then normalized by the norm of the P, right? This is what this operator does. Okay? And this equation means for massless fermions, for the right part, this helicity is always +1. So right-handedly fermions for massless case satisfy the helicity is always 1, meaning that the spin operator direction is always polar to the motion direction, right? The only in this case is +1. Okay. Okay. But for the left part, it's opposite. It's a -1. It's a minus. So this operator, the meaning of this one is the operator project the spin on the momentum. Then somebody may raise the hand and say, okay, why do you want to construct something like this? But we're always talking about, because we're now working everywhere, working in the Lorentz invariant theory, okay? We can choose different frame, okay? They might say, okay, momentum direction is not quite physical because when you switch your frame, maybe the direction changed, okay? Then this kind of definition is bad. Okay? If you are allowed to flip your motion direction for changing frame, okay, then this kind of definition is bad. You see, because this definition relies on a particular motion direction, okay, which is your momentum, the direction of your momentum, okay, which is the part of your movement direction. But we know, on the other hand, we know for massless particle this is impossible. So it's still good. So we don't talk about such kind of operator for massive part, but we do talk about such kind of operator for massless. Essentially, because for massless particle, you are not allowed to change your momentum direction by choosing another frame. It's not possible. Okay? But for massive particle, you do. This is essentially the reason we only define when we talk about the helicity for massless particle. Okay? Otherwise, there's some ambiguity for the sign, right? You don't have a definite value. If your p direction changed, if your p direction becomes -p, okay? If you're allowed to change your p to -p, then this number +1 or -1 is artificial. It's ambiguous, right? It's not a good quantity. So do you have any question about the definition of the helicity? Okay, so now some remarks. Because today's lecture, we introduced many new concept things, so you can easily get confused. Okay. For example, we have to clarify that there's a different concept. One is spin, another is helicity. Another one is chirality. Okay. All these are different concepts. Okay. So These are the different concepts. So for spin, to avoid any confusion, spin is just a vector or operator. Okay. In this case, you can just treat the sigma vector is just a spin operator. That's it. Okay, that's it. Why? Because if you remember in quantum mechanics, spin, one can define the spin is the angular momentum or rotation generator, okay, for a particle without the real angular momentum, right? But real angular momentum really means it's rotating, right? The object is rotating, right? It's rotating. There is an axis, it's rotating, okay? And we see there is an angular momentum, okay? But if the particle does not have this angular momentum, one can still define something called the spin operator, right? Some spin operator. Usually we denote it as S vector this way. So for particle does not carry angular momentum, this can be identified with the rotation generator. Okay, rotation generator. See, in other words, spin is something really intrinsic quantity. There's intrinsic rotation, right? Okay, there's no space-time rotation, but there's intrinsic rotation. Okay, if the particle does not have the usual angular momentum, one can identify the spin operator with this rotation generator, right? And then you measure it, right? I hand you some particle, some state, you can just measure it. If you can measure some non-trivial rotation charge, then congratulations. If you also, in the same time, you know there's no usual angular momentum, then congratulations, you measure the spin, okay? So in this sense, spin is some intrinsic rotation, okay? Some intrinsic rotation. But in this case, of course, we know what is J. We know what is J, right? J is the original rotation generator. We emphasize many times, J equals to J plus J minus. So, and in both cases, for spin half, this is equals to the half signal. Okay? This is the half the signal. That's why we explain. That's why we interpret this sigma vector as a spin. More precisely, spin operator is the half signal. So what about helicity? You already explained. Helicity is only well defined in the massless case, okay? And the definition of helicity relies on the spin operator. It's just the projection of spin operator and the momentum direction, okay? That's it. It's projection because it's normalized by the P, so it really pick up the projected component of the spin operator, you see, in the motion direction, right? Right? So that's helicity we just talked about. So chirality, what about chirality? Chirality is a more geometric quantity. You see, chirality almost comes from the representation. It does not depend on particular particles, you see. It's a very geometric quantity. It's not like helicity. In order to define helicity, you have to specify the mass of the particle. But for chirality, you don't need that. Chirality really just comes from the representation of the Lorentz group. You see? Okay? If your representation, the left and the right is not symmetric, then congratulations, your physical quantity has a chirality. Okay? Okay? This is the simplest case. Say we turn off left or right, we only keep the other part. So we call such representation is the half zero or zero half, okay, representation. But in general, you can talk about the half and 3 half, okay? You see, then left and right is not balanced, it's not symmetric. So in that case, you also have chirality. Okay? So chirality really means you can distinguish the left and the right. Okay? Left and the right. Now, then you might still keep asking where the lane comes from, right? we know left hand, right hand, we learned from high school, right? That means there's some handedness, right? You use left or right hand to beat it, okay? So where the left hand or right hand comes from, this kind of spinners looks funny object. Well, you can get some feeling from here, you see, right? You can get some feeling from here. In the massless case, you see, for this case, you get +1. It means what? If you understand your spin, even though it's intrinsic rotation, you think about it some kind of rotation, okay? Then there is a rotation, right? Then there is a rotation direction. And there is a motion direction, okay? Then you can try to use your right hand, okay? You can try to use your right hand to measure this helicity, right? Because you have a particle moving in this direction, okay? But then right hand means your direction or your rotation direction coincide with your motion direction. Okay, you get +1. If it's opposite, you get -1. So it perfectly fits with what you learned in high school, right? You see? Okay, so the next thing we want to discuss is related to chirality. It's also very interesting, which is how to understand the U1 symmetry in the context of the higher formula. Okay, we mentioned the U1 rotation in this case is very, very trivial. It's almost like the scalar, meaning that both left and right they're uniformly transformed. You see, does not distinguish left or right, just transform the same way. Okay, and we want to see this even more clearly. So for this, I want to discuss something called the vector or FC symmetry. Okay. You shouldn't be scared that it's lame, because the vector symmetry is just what we discussed already. It's the U1 rotation. Okay, it's the U1 rotation. For this is vector, let's put a new subscript here, V. So U1 V means the U1 rotation uniformly transform every component of the 4 cylinder, okay? Which is nothing but the phi goes to e to the minus I alpha. Okay? Okay? This is what we already talked about. We even worked out the conserved current. Okay? So for this kind of symmetry or U1 symmetry, we put another name to specify. If left and right transform uniformly, we call this is a vector symmetry. Okay? This is a vector symmetry. It's a natural name, right? Why? Because we know, for example, we know the vector, geometrically vector representation can be classified this way, right? You see? Right? It means if you both have left part and the right part, right? This is left, this is right. Then it can be equivalently to consider this is a usual vector, you see? Right? So this is indeed, this is geometric representation of the vector. Okay. Okay? So in this case, the same. If the symmetry treats the left and right completely equivalent way, just not distinguish left and right at all. You do for the left and do the same thing for the right. Okay. So in this case, we call this symmetry is vector symmetry. Okay. But sometimes, okay, so let me write it. It's important. So this means this vector V means vector. V means vector. Vector means the left and the right. expanded component transform in the same way, okay? And we even worked out the current, the conservation of the current. Let's say in this case, since we call the symmetry is V, let's put a V for the conserved current also here. So partial mu J mu in this case is partial mu psi bar gamma mu psi plus psi bar gamma mu partial mu psi. Okay, we easily check. Right? Just add, because the J mu contains this, J mu is this one. So you take a derivative. There are two pieces. Then you use the equation of motion. You know to test, to check the conservation of the leather current, we have to impose the equation of motion, right? So let's use the equation of motion. It becomes I m psi bar psi minus I m bar psi. Okay, which is certainly 0. So answer. So even for m is non-zero, as you can see, the vector symmetry is there, right? The U1 symmetry, in this terminology, the vector symmetry, U1 vector symmetry is there. Because these two terms cancel, doesn't matter m is 0 or not. Okay. Now, if we want to only restrict to m equals 0 case, there is a additional symmetry. There is an additional symmetry. Or enhanced symmetry. What is that? You can check for m equals 0, which is massless drag theory. You can check when you send the psi to e to the I alpha gamma phi psi, and the psi bar goes to psi bar e to the I alpha gamma phi. Then the Lagrange is invariant. Okay. Yeah, I already told you what is the definition of gamma phi. You can easily check. You can check this. So for m equals 0, this is a new symmetry. Because under this rotation is also invariant. From our criterion of finding a symmetry, this is a symmetry. This is a symmetry. But the property of this symmetry is they transform left and right in a different way. Okay? They transform left and right different ways. It's not like the vector symmetry. So not the same symmetry. It's not the same symmetry as before. Okay? They transform left and right differently. Why? Because gamma phi is there's a matrix structure. Okay? If you write down this explicitly, you can see this is a 4 component, it's a 4x4 matrix. You can see the left and the right transform in different ways. For example, you can write this explicitly in wire base. You can see you can write this transformation in terms of the left and the right components. And since this is a good symmetry, you can also work out the conserved current. We call this new symmetry is a axial symmetry. So we put an A index here. So this is JA mu. The conserved current in this case will be psi bar mu gamma phi psi. Okay. This is you see the conserved current is also different. This is the new conserved current. Or you can check it conserved. It's a good symmetry for m equals to 0. Okay. Yeah, you can check it. The partial mu a mu a. You can check the conservation. With the partial mu and r gamma mu gamma phi psi plus and r gamma mu gamma partial psi. This is equal to 2m I plus gamma phi. So clearly you can see when m is not 0, it's not conserved. So it's not a symmetry. It's not a symmetry. But for m equals to 0, indeed this is a symmetry. For m equals to 0, this is 0. So it's a symmetry. Okay. So this is symmetry only when m equals to 0. Okay. Then you might ask me, look, this even from the transformation property looks a little weird. You see, what was some gamma phi matrix, right? So who cares? I mean, yes. But first of all, it's a good symmetry, right? It's a good symmetry, okay? And it's the real world theory. No, it's not the real world theory, but it's a very simple theory, right? Almost the real world, okay? You ignore the mass of the electron, okay? Okay? For example, in some effective system, effective degrees of freedom, it might be described by massless fermions, okay? In either condensed matter or in nuclear physics, okay? You don't need to go to standard model, okay? You might find some system effectively described by this massless fermion. Then this is a good symmetry. You should treat it very seriously. Okay. For physics system, because we know the physical symmetry or the good symmetry have predictions. You can measure from the experiment the predictions. Okay. And another theory reason why we care this is because this is really the simplest fermion theory, and there are two. When m equals 0, there are two symmetries were established. Okay, and then there's an interesting story for some of you who are really curious about why I spent a few minutes to discuss this. Okay? Because this is heavily related with some kind of a moment. Okay? Because there's a famous story in history about these two symmetries. Okay? The two symmetry really has a property that's denoted U1V cross U1A. And this symmetry is our real world electromagnetic, okay? Because our electromagnetic dynamics coming from gauging this U1V symmetry, right? As we're very familiar. Because we couple this with photon and we introduce the Maxwell theory. Everything is related to this U1V. Okay, so this is the real world symmetry which has been gauged. Okay, which has been gauged. And the gauge field is the Maxwell field. Is that clear? It was already introduced before, coupled with photon. So this has been gauged. This has been gauged. Now there's a famous phenomenon that there's a tension between this U1V and this U1A, meaning that when you gauge this one, it must be broken in quantum level. Okay. So whenever you see, if you gauge this symmetry, that symmetry is broken in quantum level, you define it as anomaly. Because anomaly meaning the symmetry is broken from quantum effects. Okay. But this is not a precise definition. This is a very, very rough definition. in this particular example, we can make this explanation more clear. This anomaly really means there's some tension between this symmetry and this symmetry, meaning if you ditch this one, this is broken. Okay? Is that okay? So this we call that anomaly. And there's another name. Many people think that this is worth to give a Nobel Prize, but it's not yet. We're waiting for that. Someone is waiting for that. So this is for the ABJ. For the phenomenon I just introduced. Yeah. There's a real world to gauge this U1V. And indeed, if you compute the quantum corrections, you realize that this partial mu T, mu A is not zero anymore. Okay? This is not zero anymore. Okay? Because of quantum effects. Quantum potential. At this moment, we only discuss the classical level, right? See? So in history, this phenomenon was called the ABJ. ABJ then for three persons. There, Bear, Jakib. Okay. So this is the famous phenomenon. It even has some experimental test. Because in the experimental, there is a pion decay to 2 gamma. Essentially, can be explained by this ABJ anomaly. But surprisingly, ABJ anomaly did not win the Nobel Prize yet. It's a little strange. So do you have any question about this advanced discussion between these two symmetries? Okay, so in the remaining time, we have like 30 minutes. We're going to jump into discuss the Majorana fermion. Okay, Majorana fermion. Because by now we start from wire spinors. We form the rock spinner. See, and we introduce a different bases. But there's another particular interesting base or interesting object called Majorana fermion. Okay. As we already advertised the last time, why we care about talk about this such story. The question, the motivation comes from the question is it possible to make psi real? Okay. This is the question. It looks very, very simple and naive question, right? And why we even ask this question? Okay, because as mentioned last time, in general, the Lorentz transformation matrix are all complex valued. Okay, for example, in wire base, you can see it. Then there's no point to talk about the transformed object. Okay, keep the reality. Right? Because even you start from some real, the transformation metrics are all complex, then you immediately get some complex, right? Complex value object. So the reality by no means can be preserved, right? There's no point to ask in general. But in some particular case, we can ask, right? As you can imagine, if I choose some particular gamma matrix, such that the Lorentz transformation are all real values, then if you start from some real value spinner, then you can keep real, okay? Right? This is a very, very stupid mathematical logic. So to answer this question, in general, it's not possible. It's not possible in general. Because transformation matrix is the Lorentz transformation. It's complex, right? It's complex. However, there's one exception. There's one way. In general, it's possible. However, there is one way. The way is to go to Majorana base. So what is Majorana base? Let's check it. Why Majorana base does the job, right? Right? So in Majorana base, let me write down all the gamma matrix. The gamma 0 is the 0, 0, sigma 2, okay? And the gamma 1 is the I sigma 3, 0, 0. And the gamma 2 is the 0, 0, sigma 2 minus sigma 2. And the gamma 3 is the minus I sigma 1. Minus I sigma 1, okay, 0, 0. Such a particular representation of the gamma matrix. Now, fortunately, we already introduced somewhere before how to express the Lorentz transformation in terms of gamma matrix, right? Then you can easily plug in this kind of particular gamma matrix into that formula. They get some S mu nu, right? S mu nu is I over 4 commutator of gamma nu, right? So you plug into that one, you get S mu nu. Then lambda S is e to the I theta S, right? Then you plug in, you can check it indeed. For this kind of particular gamma matrix, the final lambda S is real. Why? Let me explain the reason more clear way. Because this kind of particular gamma matrix is satisfied. If you take a complex conjugate, you get minus. Okay, this means what? This means this kind of choosing this kind of particular gamma matrix looks like a pure imaginary quantity. You see, for pure imaginary, if you take a complex conjugate, you get minus sign, right? Right. Now remember that this is a pure imaginary. When you have a commutator of 2 gamma, okay, you get a real. You see, right? You get a real. Then in the definition of S mu nu, there is in front there is an I, right? Okay. Now in the unitary lambda S matrix, there is another I, right? Remember that? So all these I cancelled. All these I cancelled. So eventually you get a lambda S is real. Okay. Eventually lambda S is real for this reason. Then if you start from a real spinner, then using only this kind of Lorentz transformation, you always preserve the reality condition. Okay. This means the reality condition can be preserved. So, This means psi equals to psi star, for example, preserved. And be preserved. Okay. Now it seems this is very cheap. We mentioned last time for Majorana particle, the complex conjugate is itself, right? We mentioned last time. So this leads us to, or require us to discuss in a more clear way what do we mean by charge conjugate. Right. So in general, one can consider charge conjugation does not depend on any particular base. In this particular base, which is called Majorana base, one can easily say, okay, because this transformation is real, one can maintain this one. Then you might just take this operation as the complex conjugate, as the charge conjugation of a given fermion. Okay. But in general, a charge conjugation can be defined in a more systematic way or general way. Okay. What do I mean by that? So for a given fermion, like let's say four-spinner case, one can define a charge conjugation, which I denote as psi C equals to some C matrix together with psi star. Okay. Why we do this funny things? The reason is obvious, because if this is a scalar, okay, we all know, right? If for complex scalar, you just take a complex conjugate, that's it. You don't need to worry about anything, okay? Okay? That is the charge conjugation for complex scalar. Is that clear? So you can easily check this just flip the charge, okay? You transform some phi to some phi star, okay? You just flip the charge. But because this is a spinner, spinner has some internal structure, okay? Psi itself has some component, okay? It's not obvious. You just take a complex conjugate, it can give you the charge conjugation. It's not obvious, right? Because there are some internal structures. Okay? So for that reason, a priori we don't know, so we set some undetermined matrix here. You see? I think in general, there is some matrix associated with this, together with the complex conjugate, because the fermion has internal structures. Okay? So we define a general charge conjugation in this way, and because charge conjugation, and then we find what is the constraint. There is a constraint on this C matrix. Because the charge conjugation is a symmetry transformation. It's actually a symmetry transformation. You send the fermion to his charge conjugated partner. So C has to be unitary. So C dagger C equals to 1. And we also want to this psi C satisfy Dirac equation, precisely the same Dirac equation, right? You don't want your charge conjugated partner go beyond your equation motion. You go to some other equation. You don't want that. You want the charge conjugated partner is also satisfy Dirac equation. Okay, also satisfy Dirac equation. So that's put an additional constraint for this C. So we get C dagger gamma mu C equals to minus gamma mu star. So you get the constraint for this C. So all this and this does not depend on a particular base. Okay, it's a general discussion. Now, so if you want to go to some particular base, it means that you can find the solution of the C to satisfy this constraint. So the solution is in the, for instance, in the in the Majorana base, which we already discussed. The solution will be, the C will be equal to 1. You see? So C equals to 1, meaning that charge conjugation is indeed just typical complex conjugate, right? And but in some other base, this is not quite true. For example, in our familiar wire bases, this C will be equal to up to coefficient equals to I gamma 2. Okay. You can check it. Why? Because in principle, you can solve the C if you specify the gamma, right? In wire base, we know the explicit form of the gamma matrix. Then you find the solution. You just try to find the solution. You realize that this is the solution. In wire bases, you plug in the wire base gamma mu, this gamma mu in this constraint. Then you find that C equals 1 is the solution, right? You easily check it. Why? Because we just mentioned the wire base, for example, gamma matrix satisfies this property. You see? You satisfy this property, then you plug in to here. Then in the right hand side you get gamma mu, right? You see? The right hand you get gamma mu, right? Then C equals to 1 is certainly a solution, right? You don't need to do anything to transform the gamma mu. The gamma mu equals gamma mu, right? But in wire base, it's not true. In wire base, this is not true. Okay? It's some other relation. You plug in that gamma mu matrix to try and solve the C. So you get the solution in wire base is the I gamma 2. Okay? Is that clear? Is that clear? Because of fermion has an internal structure, in general, we cannot naively take complex conjugate for each component to realize the charge conjugation operation. Okay? Okay? A priori, if you don't know, usually you just put some undetermined matrix here, right? This matrix is a 4x4 matrix. The matrix can do the job to nicely transform your internal component, right? Then you ask, what is the possible solution for this C matrix? If I want to maintain, if I want to demand the charge conjugation partner has nice physical property, right? That's the way to think about it, right? Then you demand this charge conjugate partner satisfy the same equation of motion, and it has to be unitarity. Then you solve the C, okay? Then you find you do oppositely, you solve the C. Then you it's consistent. You get indeed in wire base you get C equals to 1, okay? And in Majorana base you get C equals to 1. In wire base you get C is non-trivial matrix is I gamma 2, okay? Is that clear? Yeah, you can derive this from equation of motion. It's not difficult. It's very easy. It's very easy. It's very easy. Okay. Yeah, let's justify this a little bit. For example, we start from the equation of motion I partial slash minus m equals to psi equals to 0. Okay? Okay? We start from here. And let's take a complex conjugate for everybody. Okay? Complex conjugate for everybody. Then I get a minus I partial slash star minus m act on the psi star equals to 0. Is that okay? This is for sure true, right? Certainly true. Now we multiply this from left by a C, okay? And this is still true. Okay. Then we use this relation. Let's check it. We use this relation, right? We use this relation. If you use this relation and use this constraint, you can easily derive from here. There is another equation is true, which is I slash minus m psi c equals 0. Okay? From here, you can get here. So this is indeed justified. Okay. The psi c, which is the charge conjugate partner of psi, indeed satisfies the same equation motion. It's an easy exercise in check. But logically, the logic is we demand that this is true. I get this constraint. Okay. That's what we get. So this is the physical requirement. Right? This is the physical requirement. Now you can do better, but this is the easy exercise you can check. You can do much better than this. For example, you can introduce. We introduced the couple with photon, right? You can introduce a photon background, which is a mu. Why? Because when you have a photon background, you can go further to see the charge carried by this, the psi of the charge carried by this psi or psi c. Okay, so we know psi and the psi c has to carry opposite charge. Okay. Now, after you introduce the coupling with photon, you can see from here you get here by using these constraints. You don't change anywhere equation motion for the psi c, but only flip the sign of the charge. Okay. So you really justify yourself. Okay, I really get this particle, which is the charge conjugation of my original particle, because the sign of the charge it flips. No, nothing else changed. Okay. Okay. You can do better than this check. Okay, so you can check yourself. So this is about the charge conjugation for fermions. Okay. So do you have any question about this charge conjugation for fermions? Of course, we also have the charge conjugation. We quite often we use C, right? Formally. We will know also there are some other discrete symmetries which call P and T, right? So putting together, there is a CPT. It's called CPT. And there is even a theorem called the CPT theorem. The theorem says that any term you can write down in your Lagrangian CPT environment. Any term belongs to Lagrangian is a CPT environment. So we don't have time to check one by one. So if interesting discussion, you can easily find it from many textbooks about the P transformation and the T transformation for fermion. Okay, for fermions. So we somehow using this charge conjugation, we get some geometric definition of this Majorana fermions, right? Because if I identify psi to psi star, in this case we know C is trivial, it's 1. So we can identify the charge conjugation with itself. You can think such kind of particle is Majorana fermion, right? But this is too cheap. This is a little cheap. Seriously, strictly speaking, to identify some physical particle with its dynamics, you can only do so, claim so, you find some kind of particle only when you know how to construct the series. Okay? Only geometry does not enough. For example, at this moment, we don't know the dynamics. We don't know the Lagrangian of this Majorana fermion, right? So this is the next step. We should specify, we should construct like Dirac fermion. We should write down Lagrangian. Only by doing that, okay, you know the physical properties, you know the dynamics of this particle. Okay, this kind of geometric definition is not enough, right? Only knowing this is not enough. For example, you don't know the equation motion of Majorana fermion. Okay, you only know this geometric information. It's not enough. So this is the next step. We want to write down the Lagrangian for Majorana particle, Majorana fermion. This is also a very, very interesting story. This to clarify this, let's go back to the last lecture. Last lecture, we spent some time to find what is the good Lagrangian term for the wire fermion. Remember that? We tried a different combination. Eventually, we find some particular combination for the environment and satisfy all the properties, all the requirements. So over there, if you still remember, we find some particular construction like I, psi, r, tiger, sigma mu, partial mu. Let me write this down. In fact, this is not a block. So let me write it in terms of wires in and fold. We find that this is a good candidate. Okay, this is a good Lagrangian in terms of wire fermions, right? Because all these are Lorentz invariant and yeah, are local and but now, however, it turns out that there is another candidate, but we didn't mention yet. There's another candidate. The candidate looks like, let's say, L1, let's say, L1 equal to psi r transpose sigma 2 r. This is also Lorentz invariant. You can check yourself. This is Lorentz invariant. This is also Lorentz invariant. I use a funny combination. Only evolve the right or left. Same thing is true for the left. I insert a sigma 2 matrix in the middle, and then here is the transpose. Okay. This is also Lorentz invariant. You can check this. Same thing is true for the left. Therefore, there is another candidate. There's another candidate to construct a good Lagrangian. For example, if I use left, then I can put I L tiger sigma mu partial mu I L plus I M over 2. I am this. I am transpose. I am. Okay? Is this okay? See? The first term is the same, right? The same what we know before, right? You see? Since I find a new candidate here is also Lorentz invariant, I can try to take use of it. See? I can try to take use of it. Now I choose to a particular combination of such kind of term. You see? You see, this is this one, right? Now you ask me, what is this? This is the complex conjugate of this one. Okay? Okay, you see it? Right? Because in general, we're not sure whether this is real. I really want to make a real combination because the reality requirement of Lagrange is also very important, right? You mentioned this, right? So somewhere I put an I, somewhere, I take a complex conjugate and combine them. All this is to make this whole thing is Hermitian. So Hermitian plus Lorentz invariant, I do find some looks a little weird, but indeed it's a good candidate for the Lagrangian. So this is the Hermitian. You can check it. Okay, you can check it. This is the Hermitian. The magic thing here is for this Lagrangian, I don't touch anything related to right part. Only that, you see. This go beyond to the original somewhere we claimed, at some point our real world really need both left and right. Remember that, right? But here, there's also looks like there's a mass term. There's also m, but everything only involves the left. It's nothing to do with the right. Okay, you can justify yourself. This is a perfectly good candidate for Lagrangian. It satisfies all the properties. So this is so-called the Lagrangian to describe the non-science. Okay, this is the non-science. Okay. You ask me how do you combine your construction here with this property here, right? On this hand, you see this is the property for the Majorana fermion. You also see this is a good theory for Majorana, how to consistent them, okay? How to get them consistent with each other. Indeed, there is a consistent check. You can do it yourself because this language, this equation is written as the 4-spinner, right? It's a 4-component. You can also write a 4-component form for this theory. Okay, so what is that? The only thing you need to do is you identify your 4-component spinner, let's say, in the wire base, with the upper half as the left, side left, and the lower half as the sigma 2, side left star. Okay, if you choose your 4-component spinner to construct in this particular way, okay, then you can check. You can check for this kind of 4-component spinner. The Dirac theory, Lagrangian, becomes this one. Okay, as you can see, it's nothing to do with the right part. Okay? Nothing to do with the right part. Only left. Only left. So, and you can further check. In this case, the psi c is indeed equals to. In this case, you can also check the complex charge conjugation. You can check the psi c equals to minus pi gamma 2 psi star, which is the charge conjugation in the wire base. Okay, in the wire base. But then there's a minus sign, but this is not important because in order to find the solution of this C matrix, the coefficient matrix here, there's an ambiguity for the overall phase. Okay, that phase is you cannot determine it exactly. That phase can pass through everywhere, right? If I shift the C, if I multiply the C by some constant phase, this is true. This is still true. Everything is true. Okay, everything is true. So there's an ambiguous phase. You cannot write the phase itself. So different textbooks choose different conventions. So okay, there's a additional minus sign somewhere, but it's not important. The phase is not physical. So C only can be determined up to a phase, C. So you can check in this particular construction. You can check the charge conjugation. Indeed, it is perfectly consistent with the charge conjugation solution. Okay. And then we found in this way we found the Lagrangian theory for the Majorana fermion. Then there are still many interesting questions you can ask yourself. What is the true difference between Dirac fermion, wire fermion, and the Majorana fermions, right? All the different questions you can try to clarify yourself. Okay. Let's check.
不是，那它它也是2分量吗？那我为什么像它那样再创造一个自由？它是2分量的，它是一个表示的话，那它是上它的
那这不是只要
结构什么的一个
和只要
对啊，
那是一样的，
这个两为什么他们两个不是独立的？
有的是区别的，两个放在一起，但是你
在外面
他俩
这是
只用了一半，
只用了一半的是我要背对吧？然后还问他这个。
因为你数学是给中伟的，被自然界体制的。
那个，如果是加好的话，这个需要的话，它也是。
或者说你还没有找那个更简洁的。
然后语言这样是吧？
这个语言的话就是一个吗？
可能是我们没有。
那如果是上半年，我这种我他现在加了一个分量，
现在有影响。男士。啊，就是我回去那个，这个是人为选的，这里人为选的感觉，
谁老师？自带感是和第一层自带有关。
第一个我注意也看，我这个地方才能更快的出来。你大概可能把这个不太差的一个
那我们也说，
因为以后才是七分的，
在那个他们在那个资源环境
都
这个呢，真正人和有心点，也就是说，小米打开那个比赛其实依然是
对，我觉得有个重要的 point 就是，我们要分清楚在什么 level 上区分不同的 part，就是这正常的意义上 trick distinguish 不够，所以你要 distinguish target 一定要 specify 到 action Lagrange， 因为只有 Lagrange 才是完整的一个讨论的意思。你光看几个 component 和这个都不够，只有 action 比较 theory，
我回去再看。
才能 specify 这个 part 是那个分析的。换句话讲，即便是同样都是图啊，我们也可以构造2种不同的理论。这个说它完整的同化才够。
就是如果我为什么想，Majorana的这个，如果假设我这个拉开，但是就是本来的话。